Hello, I'm Doug Montgomery. I'm your instructor in our Design of Experiments MOOC. I'd like to welcome you back to our monthly Design of Experiments Fireside Chat. For those of you that are new to the course or to the Fireside Chat, this is something that I do on a monthly basis. I always have a guest speaker, and we talk about specific topics, maybe from the course. Or applications of experimental design. Always try to have something really interesting that will get your attention. We leave some time at the end of the course for questions and answers. This is a great time for you to ask questions about anything you'd like. You could ask questions about the content of the Coursera courses, or if you have a specific situation that you want to ask about something that you're encountering in your own work. If you're on Coursera, we will post these Fireside Chat recordings to the courses, and you can find them in the Resources tab of your course. About the questions and about just how we run the course, please keep your mics muted and your cameras off during the session. Prevents any extraneous noise or other disturbances that might interrupt the program. If you want to submit a question, and you can question either me or our guest, please do that using the chat function on the Zoom menu. And you don't need to wait until the Q&A starts to do that. You can submit that question. You can put it in at any point during the session, and we'll try to get them answered before the Fireside Chat ends. But We'll respond to those in Coursera for those who are enrolled. For the ones that we can't get answered before the Fireside Chat ends. Our guest today is Dr. Byron Smucker, who is Associate Professor of Statistics at Miami University in Ohio. And he has a Ph.D. in Statistics and Operations Research from Penn State. He is an active researcher in experimental design, particularly practical algorithmic approaches to screening, model robust designs, and methods for the analysis of these designs. A lot of his work involves applied optimization. He has a lot of interest in statistical consulting and collaboration in areas including experimental design and predictive modeling. He's recently worked on issues of experimental design, pedagogy, statistical engineering, and subsampling in big data settings. And he's got a really interesting talk that he's going to give to us this morning. And I'm going to turn it over to him, but I'm going to ask him a question before we get started. Did you ever run into one of my former PhD students at Penn State, Enrique Del Castillo?
That's quite a question. Yes, he indeed was my advisor at Penn State.
I did not know that.
I was in the statistics department. But he had a courtesy appointment over in statistics. And,
yeah, I know he does, yeah.
I have a background. My undergraduate degree is industrial engineering. And so I saw a poster once where he was doing optimization and sort of data analysis. And I thought that sounds like a really cool area. And so that's how we connected. Yeah, he's my advisor.
Well, that's really interesting. So you are my academic grandson.
There you go.
There you go. And and Enrique has never told me this. I don't know.
Oh, there you go.
Well, I have a colleague on our faculty here, Wrong Pan, who is also one of his PhD students. So academic grandchildren show up all over the place.
No doubt.
Okay, thanks for answering that question. I should have figured it out.
All right. Well, it's a pleasure to be here. Thank you, Doug, for the introduction and for inviting me here. Today, I want to talk about, I think, a pretty practical aspect of response surface modeling, and that is if you fit a response surface model and some of the terms are not active, maybe they have large p-values, something like that. What should you do? What should you do if you want to make good predictions, if you want to do good optimization? So this is joint work with a couple of colleagues, Maria Weiss from my university at Miami, in Ohio, by the way. and David Edwards from VCU. So we work together on this project. So I want to start with a scenario. And I want you to think about what you would think to do in this scenario. So imagine you're an experimenter attempting to optimize a process, and suppose that making good predictions is what you want to do. And so you are ready to do a response surface experiment. You have 4 factors. You do the experiment, you analyze the data, but because you were unable to do a screening experiment prior to the response surface experiment, it turns out that a majority of the terms in your full second order model have large p-values. They're quote unquote not significant. So 8 of the 14 terms are not significant. So my question to you is, which would you suggest? What would be your instinct to do? Would you retain the full second order model and make predictions with that? Would you reduce the model in some reasonable way and then make good predictions, make predictions with that? Or would you say it really doesn't matter? Either way, we'll predict with about the same quality. And I'm going to actually launch a poll here. Well, let's see. Megan, I'm not sure. Trying to work with some technology here. There we go.
I relaunched it.
Okay. Yes, great. So there's a poll being launched. You can click on the poll button and answer the question. I'll give you just a little bit of time to do that. You can think about what your answer would be there. All right, so as you do that, let's continue on. So what we're going to do is basically study this question and see if we can come up with an answer, a little more general answer about what we should do in this case. All right, so a high-level overview of response surface methodology. Traditionally, there's 2 steps. I added a third step, a step 0. So my step 0 is to screen. So if you have a system that you want to optimize, if you don't already have a sense of which factors are important, then you should do some sort of a screening experiment to get down to a reasonable number of factors. Then if you are in a setting where you are far from the optimum, we typically suggest to perform some sort of a crude first order sort of model to point you in the right direction in order to make rapid improvements. And then once you get closer to the optimum within your experimental region, then you want to do some sort of second order model so that you can optimize within that region. So there's the overview, and the question we want to consider today: what if those first 2 steps are ignored? So what if the screening step and the initial improvement step are skipped over and people go straight to the optimization part? There's a paper that Maria and David and I, as well as a couple of students, worked on a number of years ago. And we actually dug up from the literature over 100 papers that had published RSM experiments. And we then reanalyzed them and sort of did a meta-analysis to understand how these RSM experiments went. But what I want to pull out from that today is more than half, well over half of those experiments that we reanalyzed from the literature failed to mention a screening experiment prior. Okay, so they did not, most of them did not screen ahead of time, which leads us to the concern that many RSM experiments are being conducted without a perhaps adequate knowledge of the system. Now, that's reading a little bit into it, and sometimes there are good reasons why you can't do screening experiments, But this is the concern. And the question that this leads to is, if we don't really have a good sense of which factors are important going into an RSM optimization study, could it be that we overfit with the second order model? That is, could it be that the second order model has too many terms for the actual complexity of the response surface? Now, overfitting is a term that we hear a lot in machine learning. Whereas if you have a set of data that you fit your model, a training set of data you fit your model to, you can really tune that and you can get a really good looking model, right? But if you've over-tuned your model to the training data, then when you test your model on an outside new set of data, then often the prediction is really poor. Excuse me. So that's called overfitting. And so we wondered if there is a similar issue with response surface methodology where screening had not been done ahead of time. So that's sort of the motivation for this work. So to reduce or not to reduce, if the goal is prediction or optimization via a second order model, should we reduce or not? Should you use the full second order model to predict or optimize, or should you reduce it? And if you should reduce, what method of model reduction should you use? So these are the questions that we are going to address today. So here are the methods that we compared in our study, okay, for prediction and optimization. So the first one is the full second order model. So if we predict and optimize using the full second order model, even if there is evidence that not all the terms are important. The second and third methods have a reduction based on p-values. So the second one is simply eliminate any terms that are, greater than 0.05 p-value. The third one is the same idea, except you adjust the p-values first for multiple tests. So the idea for the false discovery rate is that you can adjust p-values so that you can control the proportion of false discoveries that you make. You can hold that, say, to 5%. So it's a little bit more of a conservative approach, and you'll end up dropping out more terms from your model. The fourth method was forward selection. So a very classic method of model selection. And then the fifth and sixth have to do with regularization. So LASSO is a method to estimate the linear model, but it's not like least squares. It's actually a biased method where it will shrink estimates toward zero. And the interesting thing for LASSO is, for terms that it deems to be not very important, LASSO will actually shrink those estimates to exactly zero. So it's not just an estimation method, it's also a model selection procedure. And so we use LASSO as the fifth method. The Gauss lasso is a version of LASSO that uses the lasso to select the terms in the model, but those are biased because of the shrinkage. And so then there's a second step where you go back and re-estimate that model that you've selected using least squares. And so hopefully then the idea is that it'll be a less biased, better prediction. And then the last method is a method of optimization that's a Bayesian method. So the idea there is, given the data, given the model that you fit, given a prior distribution, we can derive a a posterior predictive distribution. So it's basically a distribution. Give me some X's, some predictor values, and I will give you not just a point estimate of my prediction, but I can give you a distribution of what I expect for such a response that I would observe. And this can be used to optimize. And so we include that for the optimization part. Okay, so these are the analysis methods we compared. And then how did we compare? We used a couple of measures to compare prediction quality. So absolute percent error and root mean squared prediction error. Okay, so that's how we measure the prediction quality. How do we measure the response surface, the optimization? So for optimization here, basically what we're trying to do is for any given method, we're trying to choose the levels of the predictors or the factors that maximize the predicted response. Okay, and then what we ended up doing is take that estimated estimated set of predictors that we said would optimize the response, and measure the distance between between that point, the X's, and the point in the response surface that's the true optimum. So how far away, how far away were we from the true optimal point? Okay, so the first thing we did is we sort of followed up that previous paper and found in the literature 12 papers that had validation runs and had published their response surface study. So from these 12 papers, there were a total of 25 responses. So several of the papers had multiple responses, and then a total of 54 validation runs. And those validation runs are important because they allow us to fit the model and then make a prediction and see how close we got to actual new data from those validation runs. And so we fit each of the 25 responses with each of the 6 model building methods. So just remember here, the 7th model building, the 7th method, Bayesian optimization, can be used for optimization, but the predictions from this method are exactly the same as the predictions from the full second order model. Okay, so methods 1 through 6, and here's what we found. Okay, so in terms of this average prediction error, we found that the full model seemed to do the best. Okay, and the Gauss-LASSO forward selection seemed to do okay as well. The p-value method was not terrible, but the clear outlier here is the false discovery rate adjusted p-value method. That was much too conservative. You can see the percentage of terms retained here. So it was the most aggressive in throwing out terms, over 50% of the terms thrown out, and it did not do well. So that's an initial inkling of what's going on here. Now, just keep in mind, this is a small sample, right? It's not necessarily representative of all response surface studies, but just to keep this in mind, okay? We're a little biased now against the FDR p-value method. The full second order model didn't do too bad, and so we will keep this in mind as we go forward. But the major part of the paper was a simulation study that we took, or that we constructed. And it turns out that simulating from response surfaces in a meaningful way is a lot harder than you might think. because, we have these characteristics of response surfaces that we might want to preserve, like maybe we want a maximum within the experimental region. And even that alone can be challenging to construct a simulation that will reliably do that. But we did find a paper, McDaniel and Ankenman in 2000, that gave us a response surface test bed, gave us control over effect heredity. So that was important to us. So what effect heredity is it says something like, if a main effect is important, okay, in a response surface study, then it's more likely that their quadratic effect would be important, or it's more likely that interactions involving that main effect would be more important. So that's the idea of effect heredity. Effect sparsity, so giving us some level of control over the proportion of terms that are active. And then the bumpiness of the response surface. So we have some control using this response surface test bed. We tested 15 designs, so several different central composite designs and several different box blanket designs ranging from 3 to 7 factors. For each of those, we landed on 27 settings of the test bed, of the simulation test bed. And so we ran each of the designs over those 27 settings, 1,000 simulations each, choosing an error variance of 1/2. Okay, so that's the setup. We have this response surface simulation test bed. We've got these designs that we're going to test. So a little bit more about the test bed. So the simulation, we were assuming that there was no previous screening, right? That's sort of the premise of the study, that before the response surface study, there had not been an extensive screening procedure to reduce the important factors down to just a few. So it's possible in that setting that all of the factors are active, but it's also possible that only a subset of the factors are active. So we wanted to have settings, simulation settings that accounted for both of those. And the test bed allows us to include just a proportion of terms of each type that are active. So we could get roughly at least, a certain proportion of the main effects, a certain proportion of the two-factor interactions, a certain proportion of the quadratic terms that would show up as important. We could also have a setting where all the two-factor interactions and all the quadratic terms are active. We even had settings where the true response surface was more complex than quadratic. So that would be settings where maybe it's cubic or more complicated, in which case, depending on how sort of carefully we were in the experimental region, right? If you have a complicated response surface, more complicated than quadratic, but if you're in a small enough region, you may be able to approximate it with a quadratic, or maybe not, and you will see lack of fit. Okay, so we had these different general settings of the test bed. Of course, an important part of a setup like this is we have to specify validation points. Okay, if we want to measure the quality of prediction, then we need some points that the model was not trained on. And we're going to predict those points and see how close our predictions were. So the validation points we decided on was the center run. We wanted to see how well it predict at the center of the design space. 4 randomly selected non-center runs. Okay, non-center run design points, rather. So points on the design, but not at the center. And then 4 randomly selected points from the design space. We also omitted scenarios, okay, simulation scenarios, where it turned out that more than 10% of the simulations were exhibiting lack of fit. The idea there is if you have a scenario that you are consistently getting lack of fit signal, then we don't want to predict that particular scenario because something else is going on, something more complicated needs to be fit. And so we want to limit ourselves to a population of scenarios where the fits are reasonable, okay, where the fits are reasonable. Okay, so that gives us the simulation study, what we were doing here, comparing these methods across many different scenarios, many different designs. So here's my first simulation result slide. So on the x-axis of this plot are the 6 different methods. So again, the 7 different methods. Here, we are measuring the distance from the true optimum. So the estimated optimum, the distance from the true optimum. So this is an optimization part. And so we do include the Bayesian method. And then the panels represent the different sizes of design. So a 3-factor design up to a 7-factor design. Now, I don't particularly recommend that you run, 6 or 7-factor response surface designs. If you're in that sort of situation, you really do need to do a screening experiment if possible, get you down to ideally 2 or 3. But we include this. And if you look carefully, you can see a few things. One is that the full second order model is not doing particularly well, okay, compared to the rest. It is consistently or on average further away from the true optimum than the other good methods. And what are the other good methods? Well, you can see it most clearly here in the 7-factor case. The Bayesian method is doing quite well. And the p-value methods are both doing quite well also, okay? Whereas the LASSO and the forward selection in the full second order model are doing not so well. Now, this difference is not nearly as clear in the smaller cases, but be that as it may, we do get a sense here that the Bayesian method and the p-value methods might be preferred when we do optimization. Now, shifting to prediction instead of optimization, okay, so if our goal is to make accurate predictions, here we don't have the Bayesian method. We get a little bit of a similar set of results, and that is that the p-value methods, okay, reducing by p-value, especially here the raw p-values, seem to be doing quite well comparatively. The Gauss-LASSO also does pretty well. But the LASSO and the full second order model, again, not as predictive, not as high predictive quality. Okay. So that gives us an idea looking at the raw data here. Now, this next slide might be the most important one in the talk today. So we did a formal analysis of our simulation results where we modeled, okay, in our formal analysis, the log of the RMSPE. Okay, so we were modeling the prediction quality as a function of a number of factors that we varied in our simulation. Factors related to the simulation study, but also the methods, okay, the design type, CCD versus BBD, the number of factors, the number of runs, but also a term that we're calling percent retained. Okay, so what is percent retained? So percent retained, think of it as a proxy measurement of the complexity of the true underlying model. What I mean by that is, if you have a percent retained, say down here at about 20%, that means that the true model okay, is far from the full second order model. Only about 20% of the terms in the second order model are active. If you have a percent retained up 75 or 80%, that means that the model, the true model, would be very close to the second order model. Okay, and we calculated this. It's not too important how we calculated this. You can get the details in the paper, but the results are very interesting. So what I've plotted here is an interaction plot between percent retained and analysis method. Okay, so let's try to understand this plot. So if you look at this blue line that's going off into who knows where, this is the LASSO. So when the underlying model complexity is low, meaning most of the terms of the second order model are not important, there's just a few, 20% or so, then the prediction quality for LASSO is not too bad, although it's not as good as some of the other methods. But as the percent retained gets larger and you get closer to that second order model, then the LASSO really does poorly, okay, in terms of prediction. Now, if you look at the green line here, this is an important one because this is the full second order model. So what this says is, and this makes complete sense if you think about it, for models, again, that are of low complexity, that are far from the true second order model, then the full second order model does poorly in terms of prediction. It's the worst of all the models, okay? Because it's modeling all of the terms, but the true model has just 20% of the terms in it. But as that percent retained goes toward the full second order model, it gets better and better until it's about as good as anything else when you get up to about, 75, 80% of the model's terms retained. On the other hand, if you look at the pink one, okay, the p-value based analysis method, it does the best. It does the best of all the methods when you are at those low complexity models. And by the time you get up to 70, 80%, it's right there with everything else, but it's not distinguishing itself as better. Okay, so this gives us a lot of insight into the question of when you should reduce or not. We also have some main effect plots from this formal analysis that just give us an overall view of the prediction quality. So the prediction quality, the p-value method, and the Gauss-LASSO seem to be about the best. And then we do the same thing for the distance from optimum, so the optimization part. And here we see the Bayesian method is the best, whereas the p-value methods are maybe the second and the third best among the methods. So in conclusion, so here's some conclusions just to back up and think about what we found. If you are concerned with optimization, if that's what you're worried about, then the best method that we found was the Bayesian procedure. Things that are about as good as that are the FDR adjusted p-value method or just the raw unadjusted p-value method, okay? However, we do not recommend using the full second order model for optimization if there are many inactive terms, okay? If there are many inactive terms. If there's just a few inactive terms, then it'll be okay. For the prediction, for more general prediction, then using the p-value method, the unadjusted p-value method, is the most effective, or at least is what we would recommend. The FDR adjusted p-value method and the Gauss-LASSO also are pretty decent, are fine, although we have this stain on the name of FDR because of how it performed in the empirical analysis that would make me hesitant to actually use it. Again, all the caveats in terms of the sample that we obtain from the literature may not be representative But we did observe that the FDR adjusted p-value method did not do so well in that empirical analysis. But in general, using the unadjusted p-value method for prediction will be good. So our general conclusions: the full second order model is not recommended when many terms are inactive. As the underlying true models get larger, the full second order model eventually will do fine. Will do fine in terms of prediction. So going back to our poll question, let me just pull that poll up to see. So out of the 9 people who participated, 6 of them said to reduce the model in a reasonable way, and 3 of them said return the full second order model. So based on what we have talked about today, hopefully we agree that in this case, where we actually have evidence that most of the terms are not important, then reducing the model in a reasonable way would be a good way to go. And in fact, just using the p-value, unadjusted p-values to make that reduction will give you a model that should give you good predictive quality. So thank you for your attention. And this paper was in Journal of Quality Technology in 2021. And it won the Lloyd S. Nelson Award. So we hope that it does have a positive impact in the response surface and experimental design community. So thank you for your attention, and that's all that I have.
Thank you very much. This was quite an entertaining talk. I've read this paper, and so I kind of it's sort of like reading a mystery novel where you know who did it, from
There you go.
the very beginning.
You knew the answer, yes, yes.
So I kind of knew where you were headed, and this is really kind of an interesting topic, because I can remember having some conversations on a couple of occasions with George Box about this problem, and George was a firm believer in using the full second order model. He said attempts to reduce the model are probably not going to lead to as good a results, over the long haul. And I always kind of wondered about that, because if you only have a 1 or 2 term, or a very small number of terms, model reduction isn't going to do much for you. But you do run into cases where you have a fairly large number of terms that are not significant. And Ray Myers and I talked a lot about this as we were writing our RSM book. And by the way, I'm glad you put a step 0 in, because that we talk about that too. we always said that phase 0 of a response surface study is screening. But I think the advice that Ray and I have in our book with Christine Anderson-Cook now as a co-author is pretty consistent with what you guys have in your paper and what you talked about here. But I thought it was interesting that George was firmly committed to not reducing the model.
Well, I mean, I didn't know George, and so you'll have much more insight on this. But my sense with his sort of model building strategy, I don't think he could have even imagined doing a response surface study where he didn't have a lot of knowledge of the system, right? So he would know that here are the 2 or 3 factors that are really important.
Exactly.
In which case, this model reduction problem is much less of an issue.
Okay. Yeah,
because you already know that. Yeah.
I agree with you. I think he always operated under the theory that you would be doing a screening experiment and then probably steepest descent or something like that, and then fitting your second order model. He was assuming that you would always do the classical 3-step approach.
And as with many statistical methods, you have sort of the people that have developed it very carefully. They know the context. They know, when you should do what. They're very careful about doing all the steps. But then you put it out into the wild, right? You put it out into the literature, and people, latch on to maybe the last step. And so they don't have the context as much as to why it's important to do this, the screening or the first order modeling or whatever. And then using it in the wild, people skip to the front of the line, as it were, and then things happen that they don't understand, or frankly that don't work well. Because I always like to go back to Box's books, because he has these beautiful examples, and these examples only came because he was working within a particular context, with low noise systems, sort of chemical processes, and he was a very careful modeler, building things up, empirical model building, and so his methods work very well in those cases. But when you skip those steps, they might not work as well.
Yeah. Well, the idea of skipping directly to the optimization phase, one of the places that I have seen that occur is when the person that's really responsible for this is he's a one-man team. Okay. And not only that, he's the resident expert on the problem. So he already knows what the right answer is. Okay. And that leads to different kinds of problems. Sometimes it leads to not including variables that you should include, because this person has concluded that factor is not important. I think all RSM studies really need to involve teams. You need to get different points of view. You need to get different sets of experiences involved to make sure that you're not falling victim to some of these things that can happen. There are plenty of situations out there, though, where follow-on experiments are not easy to do.
Yeah.
Some of the research work that I've done over the last 6-7 years has been with the Defense Department in experimental design for operational testing problems. And these are large, full-scale, or large experiments with full-scale systems in the field. And lots of times you simply can't do follow-on experiments. Because to do a follow-on experiment, you need access to the equipment, the people, and the range where you're going to.
It's a one shot.
Yeah, and you come back to the range management people after your first experiment and say, well, gee, we need to do a follow-on experiment.
Yeah.
And they say, well, great, the range is booked for the next 9 months.
Yeah. Yeah.
You can, we can book you early next year. And
so this is a practical problem, that it's not just people skipping the steps. It's also, practice, and with definitive screening designs, like some of these newer design ideas have built this in explicitly. Like maybe in cases where we have to do one shot, what can we do to sort of optimize, if you will,
buy some insurance. Buy some insurance. I agree. And this is another place where non-regular fractional factorial designs can be useful too, because they can help you in a single, relatively small experiment uncover main effects and two-factor interactions that otherwise you might not discover with a standard resolution 3 or resolution 4 design. Anyway, interesting stuff. This is you've really done some really nice work here, and I think it's of real value to people in the design community that do RSM. We got a couple questions, and before you and I run away with it, we ought to address the questions. This one says in the introduction, I pointed out that you had an interest in experimental design pedagogy, and so do you have any advice or resources that would help those of us who teach short courses within our companies on experimental design?
Okay, well, we do have a paper. So there's a paper with Peter Hoos, Nathaniel Stevens and Jackie Asher. So it's an international collaboration here of people who teach experimental design. And we have a paper that is just getting hung up. It should be accepted very soon to the Journal of Statistics and Data Science Education. So I would point you that direction. I'm happy to follow up. I can give you a preprint or whatever, or you can just take a look there.
By the way, I'd like to have one too.
Yeah, well, there you go.
Okay.
What we do there is we did a survey of DOE teachers in North America. We limited it to Canada and the United States. So we get a sense of what people are teaching and how they are teaching their experimental design courses. And then we each of the authors, each of the 4 authors wrote a profile of our own DOE course. Now, these are in academic settings. So the question, I think, was about short courses. So it won't be directly, applicable. I'm sure there'll be stuff that you can pull out of that. But I would point you toward Jackie Asher, my co-author. She lives and works in Israel, and she does teach at a college university setting, but she also does a lot of work with industry, and so in short courses, that sort of thing. So and I'm sure Doug has ample experience. I don't personally have experience in that setting. So a few ideas there for you.
Yeah, I've taught many short courses in industry. The way that got started is the first edition of my experimental design book was published in 1976. Edition 1 was 76, and it was at the time it was the only book on experimental design that was reasonably comprehensive, that was focused on people in science and engineering. All the books of that era, if you go back and look at them, they were all ag books. Mm-hmm. And I wrote the book because I got tired of going into my experimental design class with engineering students and say, okay, here's this experiment from this book. And they they had 4 sheep. Now, what would you do with 4 sheep? That just didn't work. Yield production, yes, yeah. Yeah, that just didn't work. And so I started going around to my colleagues in different academic departments at Georgia Tech, where I was then, and asking them, could you use some help with some of your experimental work? And I started getting these great examples, of real engineering experiments. And that led to the book. And so the book comes out in 1976. And suddenly I am deluged with phone calls from people, from companies all over the place saying, boy, this book is really cool. Would you come and teach a course? And so I had to sort of figure out how to do that. And the trick that I had to solve was how to get the technical concepts across to these folks without bogging them down in a lot of mathematics and a lot of arithmetic. Because in 76, we didn't have the computer software that we do today. I base my industry course when I teach, and I don't do this much anymore, but I've probably taught several hundred short courses in industry on experimental design. And I base it around software. I use a plug here for Jump. I use Jump, and I like Jump because it's got a lot of capabilities, and it's got some idiosyncrasies. But once you figure out the idiosyncrasies, it's pretty easy to use. I've successfully used Minitab as well, but those I think. Using that to get people through the pain of doing the arithmetic is really important. Yeah. I don't use Excel because they'd have to figure out how to program Excel, or use some add-in, and I've never seen an add-in that I thought was worth a damn. I don't use R because I don't want people writing code. The concepts are hard enough to learn without bogging them down with learning how to write code. And my own bias is to never use R, because if these people work in a regulated industry, they can't use R anyway. R is not approved by the FDA. You can't use it. And there are a lot of companies that won't let you use R anyway, because they don't want open source software on a company computer. So I stick with the what I consider to be the two, class acts of experimental design software, Minitab and Java. And I've also used Design Expert a lot too. So those are three really good packages. Another question. This is a good one. When working in a team, how do you strike a balance between incorporating expert opinion into the design and analysis process and allowing the data to speak for themselves? Any thoughts on that?
So this question's about not about the psychology of the team so much as just incorporating expert opinion into the data analysis, essentially. Is that?
Well, they're talking about both the design and the analysis process.
Okay. Well, okay, it's critical to work with the experts in the particular process that you're talking about when you're designing an experiment. I've had the experience. There's it's so easy to miss each other in terms of communication. For instance, randomization is a classic one where you just sort of assume it as a statistician or someone who's been trained in experimental design. Like you assume that everyone knows that it's important, and that when you give people a experimental design in a certain order, you wish that it's executed in that order. But people that have not been trained in these things don't have that sense. And I had an example a number of years ago where I gave them a design and they resorted it so that it was more convenient, for them to run.
I've had that same experience.
Yeah, exactly. And that actually means that we should have run a split plot experiment, and eventually we ended up doing that. So that's critical, and I emphasize to my students that it's so important that we do not come in as the statistical experts that imagine that we have all the answers and know what's going on. Because when we are working as consultants, we don't know I don't know what's going on when I'm working with my biology colleagues, my engineering colleagues. Like, they have their own expertise, and we are serving them. So I think we should take a posture of service. Now on the back end, where we're talking about data analysis, expert opinion versus the data speaking for itself. I'm a believer in data, and so I would be slow to override something that's clear in the data because someone knows better. However, it's very often the case that there is specific expertise that can help explain the results. And again, tapping into the expertise of the experts that you're working with will only enhance the finished product. But we don't have to ignore what the data is saying to do that.
Yeah, I agree. I think your point about you have to have what I call process knowledge to be able to design a good experiment. And the people that have that knowledge are not the statistical experts. But I always encourage people to do experimental design in a team, and to make sure that team has some diversity. You've got maybe the process engineer, you've got the design and development person. Maybe you have somebody from quality or the metrology group. Maybe you even have somebody that interfaces with the customer if this is a product type situation. So you've got different points of view that you want to bring out in terms of how to do the design. The last thing you want is the expert going off into a closet and designing the experiment all by themselves. because then what you will get is an experiment that's designed to reinforce their expert opinion as to what the answer is, and that often is not the best approach. I've seen that fail on a lot of occasions. Your experience about somebody sorting the runs to make it more convenient to do that, I have seen that a number of times, and that's why I've always suggested that one person on the team should always have the responsibility to make sure that the experiment is run correctly. And even to the point that you should make sure that before you start the next run, all of the knobs are turned to the right settings. I've seen that go wrong too. Lots of things.
In many ways, an experiment can go wrong, right?
Yeah, I have a long list of things to look for to make sure that things don't go wrong.
You could probably design a short course on that.
Yeah,
things that have gone wrong.
I
lessons learned.
I actually have a lecture that I do in my experimental design class on the planning process. In my textbook, I've got this 7-step process for conducting and planning and conducting experiments. And the first 3 steps are pre-experimental planning. And I spend a lot of time talking about how important it is to do pre-experimental planning, because there are things that can go wrong, and you can maybe guard against some of that by doing good planning. Another question, if in practice experimenters sometimes fit without previous experimentation, should they worry as much about factor collinearity then, about model reduction strategies, and how do these two play together? I think they're talking about the regression scenario here. If you do have a lot of multicollinearity between the variables in your regression problem, it can impact how you do model building, variable reduction. That's why techniques like LASSO can be useful in those situations. Collinearity is often a cause of poor prediction performance, for instance.
I would add there that if you are in an experimental design scenario, then multicollinearity should not be
an issue.
Yeah, because you and this is regardless of whether you've done a screening experiment or not. If you've designed like a CCD, a Bayesian design, any of the designs that we would typically recommend are expressly designed so they have little to no, correlation between the columns.
Yeah, so, most of them are nearly orthogonal, and so
yeah. So
don't have
in the experimental design setting, multicollinearity is not a problem. If you're doing something, like Doug was saying, more in regression, observational data, then that's always a concern. But then, the set of conclusions that you make is now less clear. It's less. There's not the causal,
right.
connection that you can make with an experiment. And yeah, so that's a separate set of problems from the experimental design setting.
Yeah. And collinearity can impact the way variable selection works, and that's
absolutely for sure.
It can have a big impact on that. Okay, is Megan putting another question up here? I can't tell.
We're about out of time,
and it turns out we're almost out of time anyway. Whoops, that is the end of the questions, Byron. We're done.
Okay.
I want to thank you again for a really informative talk. I enjoyed the JQT paper very much, and this talk is just great. And I would like to have a copy of the article that your team is putting together on.
Okay. We'll send that.
I'd love to have that, because I'd like to see how that aligns with some of my own ideas, and that'd be great. I'd love to see it.
Great. Well, thank you for the invitation. It's been a pleasure to be here. Enjoyed it very much.
Great. Say hi to Maria for me. Say hi to Allison for me.
Okay, will do.
Thanks a lot.
All right. Take care, folks.